This is work in collaboration with Javier Gage and Philippe. This work was initially funded by NOAA and with NSF and by NSF. And the good news is that most of the main thing I will be presenting today about tracing the origin was just accepted a couple of weeks ago, so we are very happy after 10 difficult months. Anyway, so I guess most people have seen these blooms. So in Florida as well as in the Caribbean, we are having more than before. It started in 2011. So of course the Sargassum is nothing new, but it used to be mostly on the subtropical gyre. And what is new is that after 2011, we are having blooms that covers the tropical Atlantic from Africa all the way to the Caribbean and gets also to Florida. So some people are saying that this, why the bloom started in the tropics, it was related to a big an extreme now oscillation event in 2009, 2010, and that is made possible to some Sargassum from the subtropics go all the way to the tropical Atlantic. So what we are saying is that, okay, that could be, there is some probability of that, but the first couple of things that we noticed was there was some gaps to that theory and some overlooked events that we want to point out. So the first thing is that the initial bloom from the tropics was different to the subtropics in terms of species. So Sargassum has 3 morphotypes, fluitans 3, natans 1, and 8. The Sargasso Sea mostly is natans 1, and the tropics was mostly natans 8. So there was that difference. There was a reported bloom on the Gulf of Guinea in 2009, so a little before to that now event. So that couldn't be just getting all the way there with the starting of the NOA. The other thing is that even though the records now shows comparable with 2018 and after 2011, it looked like we didn't have Sargassum in the tropics. The truth is that there was a seasonal signal from satellite much before 2011. So, and there are some in situ observations that are from the beginning of 1990. So the Sargassum was maybe there in the tropics, but it was actually in background concentrations. So what I will start is by showing our main interest was to model the motion of the Sargassum. So where it will go, when it will get there. So we started working, most of the model for Sargassum are using just passive particles with some maybe biological interactions, but what we are actually trying to add is more on the physics of the Sargassum. So we are taking into account that the Sargassum is actually floating and there are interactions within the clamps, so there are some elasticity within the Sargassum. So we started from first principles, and the idea is to consider what are the forces that are influencing the part of the sphere that is outside the water and inside the water. And once you work all your equations, you end up with a very simple equation. So the trajectories are coming from this x dot equal u, where this u is actually a combination of the current and the wind, which is actually how most people are modeling Sargassum. But the interesting thing from our way to do it is that this, the alpha parameter is actually coming from the theory and is a closed function of the buoyancy. So if we know how much of the element is above water or below water, we know what will be the parameter that we have to consider for the wind in the equation. There is another term here in the equation, and this one depends mostly on the size and also on the elasticity of the clamps. It's a smaller term, but it's very important for some of the details of how the Sargassum is organized. So I want to say that we tested and we obtained some of the parameters, and we checked the parameters in the wave tank, and we also did an optimization using satellite images and running this equation, and we have the comparison between the satellite image a month and 2 months after, and you can see that even the wave entering the Caribbean is well captured by the model. So now that we have a model that is working, we want to use this to try to see from where it's coming. So we started with a first bloom that was actually evident in 2011 in April offshore Brazil. And what we will do, we will start with probabilistic methodology. So what we will do, we divide our ocean in different grids, and we count trajectories that we did based on the equation that I just presented. And we basically count how many trajectories were in the grid I and end up in J, and so on. So you build this Markov chain and your transition matrix. Actually, in this work, we are taking into account the seasonality, so we actually have one matrix per month, and we will use this matrix to do different things that I will show in a minute. So the first thing is that, I just put it here as if we're stationary, so we are obtaining how is the distribution for the Sargassum at time n, starting for a distribution at time 0, and basically you multiply by the matrix elevated to whatever time steps you wanna get. In this particular work, we did differently, so we were using P1, P2, P3, so it depends on the month, but that's a basic, and we basically push forward the initial distribution, and you can see how it's evolving for May, June, and in July, we already have covering the whole band, the tropics from Africa all the way to the Caribbean. So, as I said, the main thing that we want to do is compare what is the probability for coming from the Sargasso Sea versus other areas, and we will see why we selected the west coast of Africa. And one thing I want to point out is that the probability in the case of coming from the Sargasso Sea is actually 2 orders of magnitude smaller than what we observe from being something internal from recirculation within the tropics. The other thing we said, okay, we can consider that the whole North Atlantic is a source, and we know what is the target because we knew when we know the bloom was there, and see what will be the probability of coming from the different places. And what we observe actually is that, again, a year or 2 years before, that was coming also from recirculation within the tropics. The next, what we did was a Bayesian inference, and for a year or 2 years and something before, you can see in black the probability, and again, what is pointed out as the strongest probability is West Africa and the Gulf of Guinea. Of course, there are other regions that has some probability to be coming from, but it's much smaller than what we are observing from the west coast of Africa. Okay, so even if it is coming from there, there are many questions. So it was always in background concentration in the tropics. There was always some amount of Sargassum in the subtropics. So something different was in 2011, why it started to bloom. So we start checking the environmental conditions, and what we observed in the area that was west of Africa, that was actually a year that was very low in temperature and high in nutrients, and that was what they call a very extreme La Nina in that area. And we also see differences in the amount of Sahara dust deposition in that particular region. So just to get to summary, we have a model that considers the physical characteristics of the Sargassum. We use that model to create trajectories, and in a probabilistic way, we found from two different methods that were independent, we found that the origin was within the tropics, close to the west coast of Africa. And okay, that is actually not in agreement what most people are saying, that was a leakage from the Sargasso Sea. Sorry. So, well, I guess questions. I just want to point out that the theoretical model is now in a Julia interface for anyone that needs to use something that is considerable size and buoyant, and not just inert particles. Okay, thank you.